This week we're going to talk about angular kinematics, both angular velocity and accelerations, and how we can apply this to body segments and body movement, and how we analyze these factors in biomechanics. Angular motion is when all points move in a circular path about the same axis, so that's really important when it comes to angular motion. And the factors that we use to describe angular motion are how far, what direction, how fast, and whether a certain segment is speeding up or slowing down. So an angle is the intersection of two lines, two planes, or a line and a plane. This is something that we touched on a little bit with our trig using linear kinematics, but angles measure the orientation of the line and the plane, and it is represented by the Greek letter theta. So we will talk about angles relative to degrees and radians, but obviously 360 degrees is a full circle, and an important conversion factor for you guys to know is that 1 radian is equal to 57.3 degrees. Now we use radians when we are relating angular to linear motion, and as I told you guys back at the beginning of this course, knowing when to use degrees versus radians is going to be crucial when you're completing your calculations in your problem set, as well on any quizzes or exams. So this is a depiction looking at the relationship between radius of a circle, arc length, and angles measured in radians. So some important conversions for you guys to know is that 90 degrees is equal to 1/2 pi radians. Okay, 180 degrees is equal to pi radian. 270 degrees is equal to 3/2 pi radians. And then, of course, 360 degrees is equal to 2 pi radians. Now, this will come into play more when we start doing our problem sets and our calculations, but this is something that you need to make note of. Write it down on your problem set packet or in your notes, but this will be important moving forward. Some conceptual components that you need to know moving forward is the two different types of angular position that we will discuss throughout this chapter. Angular position is overall the orientation of a line with another line or plane. However, in biomechanics, we often divide these into absolute and relative angular positions. Absolute angular position is defined as one line or plane is fixed and immovable relative to the Earth. Now, in biomechanics, especially with research in a lab, we usually use what's called a world axis pertaining to this absolute angular position, and I will upload a supplemental video for you to look at with that, and I'll also discuss it more in class. But with a world axis being an absolute angular position, this would be some imaginary axis, as in x, y, and then I'm just going to kind of draw it here, z, which would be the three-dimensional component, through which we would analyze mostly linear kinematics, so where a person is moving within a specific field relative to their motion relative to that axis. Now, relative angular position is more applicable to things that we will look at where both lines are capable of moving. So a good example of this is joint angles, because typically between two body segments, both segments can move in a given position relative to one another, but also relative to other parts of the body. So relative angular position is often used in biomechanics from a research perspective using inertial sensors, especially not in a lab. If you take mobile sensors to a field or some type of court, or something that doesn't have a fixed motion capture field, that will be relative angular position, and again, what we will use most of the time. Just as with linear velocities and linear displacement, we also will use angular displacement. This is the change in absolute angular position experienced by a rotating line. So mathematically, angular position is going to be equal to the change in theta equals theta f minus theta I. So typically this is going to be measured in range of motion, which is anatomical displacement in a clinical perspective. And angular displacement, in specifying direction or angular displacement, we will use clockwise and counterclockwise motion, where clockwise is indicated by a negative factor and counterclockwise movement is indicated by a positive value. The right-hand rule is utilized to identify axis of rotation, and this is a real or imaginary line about which rotation occurs and relative to the axis of rotation and is aligned with a plane. So when you're using the right-hand rule, you want to specify the plane of motion in which the object occurs, and the axis of rotation is always going to be perpendicular to that plane of motion. We will do different examples of this in class, but you want to align your right thumb with the axis of rotation in the positive direction, and then your fingers of your right hand will curl in the positive direction of that rotation. Now, I will also upload a supplementary video for this explaining how to really incorporate the right hand rule and use it, because you will need to know how to use this on quizzes and exams. So please make sure that you watch that supplemental video along with this lecture video when you're preparing for class on Monday. In discussing the relationship between angular and linear displacement, when a segment rotates, a point farther from the axis of rotation travels a greater linear distance than a point closer to the axis. So if you look at this, if we assume that this is the axis of rotation, if a point from here moves to 90 degrees versus a point further from the axis moves to 90 degrees, this further point is going to have a greater arc length, okay? So this is mathematically represented by arc length, which is basically a square, equals delta, or change in theta, times the radius r. Now this is a good depiction of the relationship between linear and angular displacement from an anatomical perspective. What's really important, and this is listed on the previous slide, is that your theta must be in radians when doing calculations, and your r, or your displacement, the linear displacement of the endpoint, must be in meters. So please remember that when we're going over our problem sets and when you're studying for the quiz for this chapter. Angular velocity is defined as the rate of change of angular position. So this is how fast a body is rotating about an axis and can be expressed in degrees per second or radians per second depending on the problem. Now mathematically, this will be written as angular displacement equals change in theta in degrees divided by the change in time in seconds. An important term that you need to know, especially when you are reading problem sets, is instantaneous angular velocity. And this is defined as the rate of rotation at a specific instant in time. So this is not the rate of rotation over a full range of motion or a full movement, but at an instant in time, particularly at a specific angle, so a specific value of degrees or radians depending on the problem. A couple of important conceptual points with the relationship between angular velocity and linear velocity is that points farther from an axis of rotation travel a greater linear path than points closer to an axis of rotation in the given same amount of time. Okay? Points farther from the axis of rotation travel at a greater linear speed and greater instantaneous linear velocity than points closer to the axis of rotation. So the second conceptual component of points farther from an axis of rotation traveling at a greater linear speed than points closer to the axis of rotation can be mathematically represented by v sub t equals angular velocity times the radius. So v sub t is going to be your instantaneous linear velocity tangent to the circular path in meters per second, and angular velocity is going to be the instantaneous angular velocity must be in radians per second, and r is the radius of rotation. Now, to further describe tangential linear velocity, as we stated in the previous slide, the magnitude is going to be v sub t equals angular velocity times r. Now, this is described or depicted as if you have an axis of rotation here in the center, okay, this is your radius, and you have a point moving along this circular path, the tangential linear velocity is going to be, if this object were to leave this circular path and be projected along a linear path, this is the velocity that we are looking at. So this is important, especially in biomechanics and exercise science, because we think of a lot of sporting activities having this tangential linear velocity component. If you think about a baseball pitcher or softball pitcher, a shot putter, discus thrower, all of these athletes or types of motion, the tangential linear velocity is going to be very important in their performance and their effectiveness as an athlete, right? And ultimately, this tangential linear velocity depicts how fast and in what direction the point that is moving, so the point that is moving along this angular path, at an instant in time. So that is all we have for the first part of this lecture. Please make sure you watch the supplemental videos that I upload for the right-hand rule, especially prior to our next class.